Somewhere beyond the last planet you were taught to remember, there is a world made of storms. Not the gentle kind, not the photogenic kind, the kind that moves at 2,100 kilometers per hour, winds faster than the speed of sound, winds faster than anything else in the entire solar system. And they blow on a planet so far from the sun that it receives almost no heat to drive them. We have almost no idea why. We visited Neptune exactly once. A single spacecraft traveling for 12 years passed by in a matter of hours in 1989 and kept going. Everything we thought we knew about Neptune, we learned in one afternoon. And even then, what we found made no sense. Neptune is the planet we forgot. The distant one? The blue one? The quiet one sitting at the edge of the solar system, too far away to bother with, too cold to matter. We were wrong about all of it. Let's start with the winds, because nothing prepares you for them. On Earth, a Category 5 hurricane moves at around 250 kilometers per hour. That is the upper limit of what our atmosphere can generate. It tears roofs off buildings, it levels entire coastlines. Neptune's winds move at 2,100 kilometers per hour. That's not a storm. That's the default state of the planet, the baseline, the calm between the violence. And it's happening on a world that receives 900 times less sunlight than Earth. There is almost no solar energy reaching Neptune. Sunlight there is as dim as a cloudy afternoon on Earth seen from a distance of 4.5 billion kilometers. And yet somehow, from somewhere inside the planet, an engine is running. We don't fully understand the source. Neptune radiates more heat than it receives from the sun, significantly more, which means there is something generating energy in its interior that our model still can't fully account for. A frozen giant that shouldn't be able to sustain violent storms sustains the most violent atmosphere in the solar system. That's not a metaphor, that's a measurement. And then there is the Great Dark Spot. When Voyager 2 flew past Neptune in 1989, it photographed a storm system in the southern hemisphere. Dark, oval, enormous, roughly the size of Earth. A planetary-scale hurricane. Scientists named it the Great Dark Spot, a clear echo of Jupiter's Great Red Spot, which has been raging for at least 4 centuries. The assumption was that this storm was similarly ancient, a permanent feature, a scar. 5 years later, the Hubble Space Telescope looked at Neptune, and the Great Dark Spot was gone. Not weakened, not relocated, gone. And in its place, in the northern hemisphere, a new dark spot had appeared. We still don't know what this means. We don't know if these storms form and dissolve on timescales of years or decades. We don't know what triggers them or what ends them. We have one data point from one flyby and 35 years of Hubble images that have raised more questions than they've answered. Neptune is not understood. It is observed. There is a difference. But the atmosphere is only the beginning. Go deeper, past those screaming winds, past the cloud bands of methane ice that give Neptune its electric blue color, and the pressure begins to climb. The hydrogen and helium of the upper atmosphere give way to a region of superhot compressed water, ammonia and methane, not quite solid, not quite liquid, moving in slow convective churns under conditions that exist nowhere else in the solar system. And deeper still, there is a theory. Under pressures millions of times greater than anything at Earth's surface, methane molecules are thought to break apart. The carbon separates from the hydrogen, and under those conditions, that carbon may compress into crystals, diamonds, raining downward through the interior of Neptune, sinking slowly toward the core, accumulating. The planet may be generating diamonds continuously, falling like slow precipitation through an ocean of pressurized fluid toward a solid core the size of Earth. This has not been directly observed. Neptune's interior remains invisible to us, but the physics are considered plausible by the researchers who model it. A world that looks like frozen vacancy from the outside may be raining diamonds on the inside. Now go to the edge of the planet. to its moons. Neptune has 16 known moons. Most are small, irregular, and unremarkable, but the largest, Triton, is one of the strangest objects in the solar system. Triton orbits Neptune backwards. Every other large moon in the solar system orbits in the same direction its planet rotates. Triton orbits in the opposite direction. This is called a retrograde orbit, and it is considered strong evidence that Triton did not form around Neptune. It was captured. Something, a gravitational interaction in the early solar system, sent Triton into Neptune's gravity well, and Neptune held on. The cost of that capture was catastrophic. Before Triton arrived, Neptune almost certainly had its own system of moons, bodies that had formed in orbit, as moons normally do. When a large retrograde object enters an existing moon system, the dynamics become violent. Orbits destabilize. Collisions occur. The original moons were likely destroyed or ejected over millions of years. Triton is the only survivor of whatever existed before it, and Triton itself is dying. Its backwards orbit means it is slowly losing energy to tidal friction. It is spiraling inward, imperceptibly by human timescales, but measurably. In approximately 3.5 billion years, Triton will cross the Roche limit, the point at which Neptune's gravity becomes stronger than the structural forces holding Triton together. The moon will be shredded. Its fragments will spread into a ring system that may rival Saturn's in beauty. Neptune will have destroyed its own moon, pulled it apart, worn it down, and in its death, that moon will become the most spectacular feature of the planet that killed it. We know this is coming. We know the timeline, and we can do nothing but watch. Neptune has been alone at the edge of the solar system for 4.5 billion years. One visitor, one afternoon, one flyby at 17 kilometers per second, transmitting data across 4.5 billion kilometers of empty space before Voyager 2 kept going, past the heliosphere, past the boundary of everything the sun can reach, into interstellar space, where it still travels today. We have not sent another mission to Neptune. There is no approved mission to Neptune. The next window to use Jupiter's gravity to accelerate a spacecraft outward, the kind of shortcut that made Voyager possible, opens in the 2030s. If we miss it, the next one is decades away. We know less about Neptune than we know about the surface of Mars, less than we know about the cloud tops of Venus. We have one afternoon of data and 35 years of questions. The furthest planet in our solar system may hold answers about how gas giants form, how planetary systems evolve, how storms can exist without heat, and whether the conditions we consider extreme are actually more common in the universe than anything we experience here. We just haven't gone back to ask.